Okay, so let's do some more practice with some point charge electric fields. Here we have a couple charges, Q1, Q2, 0.19 nanocoulombs, negative 0.26 nanocoulombs, 7.2 millimeters between the charges, and then 6 millimeters to the left of Q1. This is where we are going to find the electric field. Okay, so this is the same type of thing as before. We just have a couple charges, find the electric fields from the charges and put them together. That's all we're going to do. Okay, so I'm going to start with the electric field for number 1. If I find that, I'll do KQ1 over radius 1 squared, and I can find the electric field from Q1 at that location. And that'll give me 4.75 times 10 to the 4 newtons per coulomb. The electric field will be going away from the positive charge, so at this location, it'll be going towards the left. Okay, now I'm going to do the exact same thing for Q number 2, the electric field for number Q2. So KQ2 over radius 2 squared. I got the K, the Q2, I know that. The radius will be the combination of those two values put together because the Q2 is 13.2 millimeters away, so I'm just going to add the two distances together, and I can find its electric field. And that will give me 1.34 times 10 to the 4 newtons per coulomb. The electric field wants to go towards the negative, so just pretend Q1's not there. It's going to go towards the Q2, so it's going to go this way. And I mentioned this before, I know I'm probably right with my answers because my powers of 10 are very similar, so things are looking pretty good. All right, so now I'm just going to take these two and I am going to just put them together. I've got the 4.75 going towards the left, and I can just subtract the 1.34 from it, and that gives me a total electric field at that location. Altogether would be around 3.41 times 10 to the 4 newtons per coulomb. Going to the left is winning, so it would be to the left. So that would be the electric field at that location. Okay. All right, well, let's take the situation. Let's just modify it a little bit, switch some things out around a little bit, and we'll see what we can do here. Okay, so I'm going to delete this part right here. I'm going to delete that, and I'm going to get rid of. Well, you know what? We'll just start a whole new question altogether. It'll be a little bit easier. All right, let's just start a new question. Okay, so let's get rid of this as well. Delete. Okay. So let's start with this. Suppose we have a positive charge, Q1, and let's say Q1 is 0.72 microcoulombs, and over here we are going to have another positive charge, and we do not know the value of that positive charge. Or you know what? Let's just do let's just get the value for it. Let's say it's 0.56 microcoulombs. All right, and we're going to piece a couple things together here. And let's say that, you know, let's switch it up. Let's switch it up a little. Let's get rid of this. We can actually, we'll try and find the Q instead. A little more interesting that way. So we don't know the Q. We'll try and solve for it. And what we're going to say is at this location right here, I'll even use red. At this location right there, the electric field is equal to 0. Okay, and let's say that this charge here, Q1, let's say this one is 0.46 millimeters away. Okay, so the electric field at this location is 0, and this is 0.46 millimeters away. This guy's creating an electric field, so is this one. And let's say this one is 0.32 millimeters away. And what we're going to do is we're going to try and find Q2, so the electric field at that location is going to be equal to 0. Well, they're both giving off electric fields. The electric field from Q1 would be going towards the right, the electric field from Q2 going to the left, and obviously they are canceling out. So the two electric fields have to be equal to each other. So I can find it for Q1 and then just move to Q2. Now, the point is closer to Q2, So I know the Q2 does not have to be as large to have the same effect because the point we're interested in is closer. But let's see if we can work with this. So let's just start by finding the electric field from number 1. So that'd be KQ1 over radius 1 squared. And I can find the electric field from that one first. And that gives me 3.06 times 10 to the 10 newtons per coulomb, and it would be going towards the right. So that tells me that the electric field for number 2 has to be 3.06 times 10 to the 10 newtons per coulomb going to the left in order to cancel this one out. So this would be equal to KQ2 over radius 2 squared. And the only thing I don't have is Q2. I've got my second radius, I've got my E. I just have to rearrange this to solve for my Q. So Q2 would be E2 R2 squared divided by K. And I can solve for the second charge. And I know it should be less than 0.72 microcoulombs because it is closer to have the same effect. So I should get around 3.5 times 10 to the negative 7 coulombs. And if we put that in the same notation with the micro, so that is 0.35 microcoulombs, which is smaller than Q1, which is what I was expecting. So there's my second charge. Okay, so that is how to do a question like this. All right, well, let's get rid of these guys a little bit and see what else we can find in a different type of question. Okay, so we have a 2-charge setup, and we're going to find the electric field at this location right here. We've done a question sort of like this before, but it's basically find the 2 electric fields and just put them together. So I'm just going to start by finding the electric field from my first charge over here. So electric field for number 1 would be KQ1 over radius 1 squared. I have everything I need. I'll end up doing the same thing for this one. Electric field number 2 will be KQ2 over radius 2 squared. So I'll just calculate my 2 individual electric fields, and then we will just put them together. All right, so for the first one, I should get around 2.8 times 10 to the 8 newtons per coulomb. And for the other one, I got like 3.75 times 10 to the 8 newtons per coulomb. Again, my power is 10, but orders of magnitude are about the same, so I'm probably good to go. Okay, so if I go back to E1, this is a positive charge, so the field would radiate away from it. So at this location, it would be going towards the right. And for my charge number 2, it's negative, so the field would go towards it. So that field should be going down. So I've got a field going this way from number 1, and I've got a field from number 2 going down. So of course they are going to make a triangle. We've done this type of thing before, so it's got to put them together. So from E number 1, I've got 2.8 going to the right, and then I've got 3.75 going down, and the total electric field would look something like this. So I'm just going to take that 2.8 and square it, and then add that 3.75 together after I square it and put them together. And then I can use Pythagoras to find out that this is around 4.7. So my electric field would be 4.7 times 10 to the 8 newtons per coulomb at, we need the angle as well, of course, so inverse tan would work really nicely for that. So we'll use the 3.75 and the 2.8, and then we can find out that the angle in there is around 53 degrees, and since it's going down, we'll say negative 53 degrees. So that would be something like this. Now, this actually makes sense, because if I asked you guys to draw the electric field between these 2 charges, you guys would draw something like this. You go on pause negative, something like this, and you do this. And when you came this way, it would look something nice, something like this. That's what you guys would draw. And at this location right here, that answer that you guys just found, this answer right here, would actually be tangent to the electric field curve that you actually would have drawn even in grade 11, because you guys would draw it to come out like this, like this. So last year in grade 11, you drew these fields all the time. Now you could actually calculate the exact quantity and how big the fields actually are, as well as the actual direction they'd specifically be going in at any location. So it just enhances what you guys already started looking at in grade 11. Okay. Now, speaking of enhancing, let's see if we can also extend on your knowledge of electric fields from point charges and move on a tiny bit into sort of like the next step. So what you guys had done so far is you basically, we've had charges, and there's a charge, and the charge gives off an electric field all over the place. And you guys have done, calculating the electric field is KQ over R squared. This is what you guys have been doing. Now, what if we then incorporate a little charge at that location? Well, if you put a charge at that location, that little charge will experience a force. So again, very similar to gravity. So to calculate the force on it, you guys have done this before. You guys know how to calculate electric force is equal to Q times E, which is what you guys did a whole bunch of in grade 11. Now, the only difference is in grade 11, that electric field was typically a nice parallel plate, and we did some of that in grade 12 as well. But when there's point charges, it's not a uniform electric field. So what we can do is we can take this and we can put it into there, which then takes into account the changing electric field from the point source. So if we put that in there, it then becomes Q, and then we got the KQ over R squared. And we just sort of clean this up a little bit, and you end up with KQ over R squared. So there's our KQQ over R squared. And that's how you can calculate the force between two charges. Now, this should look really familiar, because when you guys did gravity, the force of gravity was GMM over R squared. It's literally the exact same type of calculation, except using charge values instead of gravitational values. So again, the calculation is very similar. How the field works and applies forces is very, very similar. And we can do the very similar type of calculation. Again, one of the key differences is that we can often have more than just two things. Like with gravitational forces, typically it's two things. Typically we're talking like a planet, a moon, and everything else is too far away. But with electric forces, you can calculate the force between two things, but sometimes it could be three or maybe 4, 5, 6. You can have as many as you want because subatomics can be really close to each other. But anyway, so the calculation is very, very similar to what you guys did with gravity. It's KQQ over R squared. That's how we'll calculate the electric force between charges. And we'll be practicing that next.